that logarithms and exponential functions are inverse functions. So that means one function undoes the other function. So keep in mind how the graphs of inverse functions are related, and they're related by reflecting over the line y equals x, hence my really bad joke in the beginning. So let's take a look at just a basic log function. So right now the base really is pretty arbitrary. This is going to be a base 2 function just because our exponential functions were base 2, so it'll kind of play off of those tables that we worked with. But for the most part, it can be any base that you want. It is going to change your values a little bit, but the bases doesn't really make a big difference here. So to graph this, we are going to make a table of values. And before I do that, I want to do a little bit of work because it's kind of hard to pick values that might make my table look a little bit nice. So I might do a little bit of effort here. And I'm going to replace f of x with y equals. And then I'm going to go ahead and rewrite this in its exponential form, in its equivalent exponential form. So that's going to be 2 to the y power is equal to x. So this statement and this statement are completely equal to each other, but this one, the second one, is going to be so much easier for me to graph. So what I'm going to do is I typically, when I make graphs, I determine the independent variable, the x value, and then I figure out y based on x. But in this case, since my y value is up here in the variable, like in the exponent up there, I'm actually going to have the y be the value that I pick, and then I'm going to determine what my x value will be based on the y value. So this is kind of like the only time we've ever done this before. So we can pick some values. You could pick -3, -2, -1, kind of the same values that we picked with the exponential functions, and we can go ahead and plug them in. 2 to the -3rd power is 1/8. And then we'd get 1/4, 1/2, 1, 2, 4, and 8. So since these two are equivalent expressions, since this first one and then my equivalent exponential here are equivalent expressions, this table is way easier to come up with than it is to try to pick my x values for the original logarithmic function and try to graph them from there. So what I'm going to do now is I'm just going to do my best point plotting here just to see what I'm going to end up with. And so here's what my logarithmic function is going to look like. It does something like this. And if you recall what that exponential function looks like, I'll just kind of roughly sketch this in pink just so you can kind of see. There's my exponential function, and hopefully you would believe me that these two are going to be, these two functions would be reflected over this line right here, y equals x. You can definitely kind of see that, that reflecting that's happening. So we do have the inverse here of our exponential function, and we did use an exponential function to help us graph this by rewriting the original log function in its equivalent exponential form. So notice if we were actually finding the inverse function here, we would have swapped x and y before, and then we would have solved this equation for y. So let's look at this. Let's go back and look at this blue function right here. This function is log base 2 of x. So let's answer a few questions about it. These questions you're probably getting sick of seeing, but here they are. So let's take a look at what we have. Let's start with the domain. So notice here, I do have some domain issues. My x values can get really, really close to 0, but they can never actually equal 0. I'm asymptotic to that x equals 0 value because I can get really, really close to it, but I can't actually ever equal 0. So for my domain, I'm going to be 0 to infinity. My range, however, since my y value is my exponent, I can pick anything that I want for an exponent. So my range is going to be from -infinity to infinity. My asymptote here, since it is a vertical asymptote, I'll go ahead and sketch that in here. This is my vertical asymptote where every x value is equal to 0. So notice that's relating back to my domain value because that's what I have to be careful with. I can't take the log of 0 and I can't take the log of a negative number. So at x equals 0 is where I get that asymptotic behavior. Where do I have intercepts? Well, since x will never equal 0, I'm not going to have a y-intercept, and you can then look in the table and see where your x-intercept is going to be. And notice, if you kind of want to relate this back again to our exponential function, the exponential function, the domain and range here were flip-flopped, right? Since it was the exponent, the x was in the exponent spot, your domain was negative infinity to infinity, and then your range was 0 to infinity. So notice we flip-flopped them here, and then notice the asymptote has also flipped. For the exponential, we had y equals 0 for the asymptote, and so for our log function, we have x equals 0. And then also note that the intercept flip-flopped. We had 0, 1 for the y-intercept for the exponential function, and now we're looking at 1, 0 for the logarithmic function. As far as end behavior here goes, we'll just kind of look at what it's doing. Since x doesn't approach negative infinity, what x does do is x approaches 0. So maybe we'll just kind of work with it that way. As x approaches 0, what is y doing? Well, y is going down to negative infinity. My y values are getting really, really small. And then as x approaches positive infinity, my y values are getting bigger. So they are approaching positive infinity. As far as intervals of increase or decrease or constant go, if this was a little bug on my graph, as it's walking along left to right, my y values are increasing. So we are working with intervals of increase, and it is over the domain of the function from 0 to infinity. And then there is no symmetry. Now let's talk about transformations of a basic log graph. So what if we wanted to look at log base 2 of x plus 2? So we would know that this plus 2, since it's outside, it's not in parentheses with the x, this is going to move my graph up 2. And notice I just have copied over my table from the original log function. So anytime I want to graph a log function, if I have all these transformations applied to it, I would want to go back and just figure out my table values for this original function right here, so log base 2 of x, and then I would apply my transformations to them. So this is exactly what we did. We did this first part, the part in the box in the previous problem. Now I want to shift it up 2. So if I'm going up 2, that means that's going to affect all of my y values. So my y's are going to increase by 2. So let's go ahead and add 2 to each of these values. And then these will be my new ordered pairs to graph. It's that easy. Start with that base table, and then you can just plot those new ordered pairs. So now my first point would be, I guess I didn't put 1/8 comma -3 in here. I started with 1 above, but we can still make this work. So there's 1/4 0, 1/2 1. And so you can see, here's my new log function, and it's been shifted up 2 units. Now, what's changed from the original, we'll call log base 2 of x, the original kind of parent function or base function here? Domain and range haven't changed. Looks like maybe the only thing that's changed here have been the intercepts. So this one now has an intercept here. I can see it in my table, so maybe we'll just make note. We have an intercept at 1/4 0. If you want to see this algebraically, since this is an x-intercept right here, that means your y value is set equal to 0. So I get that. I'm going to go ahead and subtract the 2 to the other side. And then this is where you get a little stumped, and this is what we'll talk about in our next lesson, is how to solve these kinds of equations. But here it's really kind of cool. Since I don't know what to do in this log form and I've got it as simplified as possible, I can go ahead and rewrite it in its equivalent exponential form, and then that's going to help me figure out what I'm going to get. So this would be 2 to the -2nd power is equal to x. So that's where my 1/4 is coming from. So kind of cool. All right, what if we have something like this? What if we want to transform our function 2 units now to the right? So that minus 2 inside with the x, notice the parenthesis difference between this one and the last one. This is now moving my graph to the right 2 units. So how do you move something to the right 2 units? Well, that's going to affect your x values, and so I'm going to add 2 to those x values. So I'm just going to take 1/4 and add 2. Take 1/2 and add 2. And so now I have my new ordered pairs. And it should still resemble an exponential function, or sorry, a logarithmic function, because it is. You're just moving it around on the coordinate plane. So with this one, I do have a new domain. So my domain has changed, my asymptote has changed. Notice when you move it to the right 2 units, now I'm looking to see what would make 0 inside here with the x. Well, 2 is what would make 0. So I need to make sure I stay bigger than 0. So my domain is now going to shift from 0 to infinity to 2 to infinity. That moves my asymptote to x equals 2. The asymptote and the domain for our log functions are always related. And then notice this is also shifting my intercept here. So I have a new intercept, it looks like, at the point 3, 0 for that intercept. So that got shifted to the right 2 units as well. It was at 1, 0. All right, what if we have lots of stuff happening? What if we have this kind of double transformation thing happening? So what's going on is we're going to be moving our graph to the left 1 unit, if that's +1 inside with the x, and then we are moving our graph down 3 units. So left 1 means we're going to take away 1 from the x coordinate, and down 3 means we're going to take away 3 from the y coordinate. So again, I'm going back to that base function. This is my table for y equals log base 2 of x, and then from the table I can easily apply these transformations. Now when you are subtracting things away from your x value or from your y value here, it is going to be that value minus 1. So this is going to be 1/4 minus 1. So this will be -3/4, and this will be 1/2 minus 1, and 1 minus 1, and 2 minus 1, 4 minus 1, and 8 minus 1. So there's my new x coordinates. And then for my y coordinates, again, I'm going to take away 3 from each of these. And then these will be my new ordered pairs. So that would be my first ordered pair, -3/4, comma, -5, -1/2, comma, -4. Those are going to be my new ordered pairs. So I'm going to take a second here and get these guys plotted as best as I can. Oops, I had a bit of a rogue point on there. But hopefully you can look at this graph and compare it back to our original function. It has moved to the left 1, and then it has moved down 3. Now a lot of things here have changed. We do have a new domain. Because I had a horizontal transformation here, that definitely is going to affect my domain. It looks like now my x values are getting really, really, really close to -1. So my domain is going to be from -1 to infinity. My range hasn't changed. It's still going to be -infinity to infinity. If I shift that down by 3 units, it's still covering all real numbers. My asymptote has moved. That's going to be now at x equals -1 because that's going to be tied into my domain. And then let's look at our intercepts here. I do have 2 intercepts here, actually, it looks like. So if I look at my first intercept, I can see I have a y-intercept. So that's going to be when my x value is 0. So x is 0 and y is -3. I have that intercept. And then it looks like I have this x-intercept over here at 7, 0. So my intercepts here have also moved. So that's basically how you graph logarithmic functions. They should hopefully be pretty straightforward. Just start with that base function and then apply the transformations to that table. One more thing to talk about before you guys try the homework is just looking at some domains. So we're not going to graph these log functions, but I just want to talk about them because they can be a little bit funky. So the big thing to remember is that the argument for your log has to be greater than 0. So when you have some, like say this first one, that look a little bit funky, like this, I just want to take that and figure out, okay, that has to be greater than 0. So set it greater than 0. And then let's do some solving to see what our x value is going to be. I'm going to go ahead and add 3x to both sides. You could certainly subtract the 1, but you just have to remember when you divided by the -3 that you would need to flip-flop that inequality sign. So then I get 1 is greater than 3x, so then I have to divide both sides by 3. And that tells me then that 1/3 is greater than x. My brain likes to see it rewritten. I like to have the x first. Just make sure here, when I do rewrite it, the inequality sign is open towards the 1/3. So when I rewrite it with the x first, the inequality sign is still open to the 1/3. So this means my domain, x is less than 1/3. My domain is going to be from -infinity to 1/3. And you can kind of just, even test in some values. If I plugged in, say, 0, that would be something that would fall within this domain. 1 minus 3 times 0 would be 1 minus 0, which is 1. I can take log base 4 of 1. It might be an ugly value, but I can certainly do that. Now, let's look at the second one. B is probably the nicest one on here. So 2 plus x. So you can figure out, okay, what's going to make 0 here? This one's a lot more obvious, I think, just by looking at it. If it's not, again, you could still take whatever's inside the argument and set it so it's greater than 0, and then solve this equation. So I would take away 2 from both sides, so x has to be greater than -2. So this would mean my domain is from -2 to infinity. Now, C by far is going to be the trickiest. It makes no difference that this is natural log. That is not what makes this tricky. Notice here, I didn't care that this was log base 4 or log base 2. I essentially ignored it because it doesn't matter. It can be log base anything. I just care about what the argument is and making sure it's greater than 0. So I don't care that this is natural log. That's not what makes this tricky. What makes this tricky is the fact that this is a quadratic inside of here. Now, we'll spend one of our last days of this semester doing interval testing. So we kind of might as well get a little introduction right here because this will be something that'll be super useful to you guys in calculus. And I'm kind of treat it the same way as A and B, but a little bit different. So I'm going to take the argument, so x squared minus 64, and I do want that to be greater than 0. Now, solving a quadratic inequality, I can't just, add 64 to both sides and factor and do all that. What I'm going to do is I'm going to find what's called critical values. And I do that by setting this equal to 0 and then solving the equivalent equation. And that gives me the numbers that either A, make the denominator 0, so makes the function undefined. That's not an issue here because they are quadratic. So my domain with a quadratic function is all real numbers, but it does help me figure out where the zeros are going to be. So I'm going to go ahead and solve this equation. You could solve this by factoring. You could solve this by adding 64 to the other side and using the square root method. Either way is going to generate these two values of +8 and -8. And again, I just want to introduce this vocabulary. These are called critical values. So what's going to happen here to help me determine what's going to work and what's not going to work is I'm going to take these two critical values and I'm going to plop them on a number line. So -8 is right about there, +8 is right about there. Notice I'm not adding any other numbers on here. I don't even have 0 as like an orientation point. What I'm going to do is this offers me 3 areas to test a number and see whether or not it works, because I'm not sure which interval of x values will make this inequality true. So I'm going to test a value. So I'm going to pick a value that's going to fall to the left of -8. And I'm going to be super crazy and let's test x equals -9. You can pick anything you want. Pick -100, pick -8.1. That's your choice, but make your life a little bit easy and pick something that's nice to work with. And so what's going to happen is this number is going to get plugged back into my original inequality right here. And I'm going to see whether or not I have a true statement. Because remember, I need to maintain that argument as a number that's greater than 0. So I'm going to plug in -9, and that gets squared. So is -9 quantity squared minus 64, is that greater than 0? So is 81 minus 64 greater than 0? It totally is. Whatever that value is, I'm off the top of my head, I guess what, 17? It is certainly greater than 0. So that tells me that this interval to the left of -8 works. I'm now going to move on and test my next interval. So I'm going to test somewhere between -8 and 8. Again, it's your choice what value you want to pick. I like to test 0 wherever that interval falls because it's typically an easy one to plug in. So let's see what happens. Is 0 squared minus 64, is that greater than 0? Well, this would be -64 greater than 0. That's false. So that tells me that this interval in the middle doesn't work. So I cannot have values between -8 and 8. So then let's look at our third interval. So let's pick a number that's going to be to the right of +8. So how about we test x equals +9? So is 9 squared minus 64 greater than 0? So is 81 minus 64 greater than 0? Absolutely. So this interval here works as well. So what that tells me is this interval works for my domain and this interval works for my domain. So we would say, what's the domain for C? Well, long story short, it's going to be from -infinity to -8, not inclusive, union 8 to infinity. So I want to get rid of that -8 to 8 chunk or interval. And notice I'm not including -8 or 8 in my domain because both of those values are what makes 0. So if this part C was a little bit crazy, don't worry, we will do a full day with interval testing as part of our calc prep at the end of the semester. But there it is. There's graphing logarithmic functions and looking a little bit at their domains. I hope this helps.